This video is a step-by-step solution for the example entitled Evaluating Refrigerator Performance. In this example, you will learn about computing the actual coefficient of performance of a refrigeration cycle and comparing it to the limits imposed by the second law for a system undergoing a refrigeration cycle with specified temperatures. Let's look at the problem statement as provided. By steadily circulating a refrigerant at low temperature through passages in the wall of a freezer compartment, a refrigerator maintains the freezer compartment at -5 degrees C when the air surrounding the refrigerator is at 22 degrees C. The rate of heat transfer from the freezer compartment to the refrigerant is 8,000 kilojoules per hour, and the power input required to operate the refrigerator is 3,200 kilojoules per hour. Determine the coefficient of performance of the refrigerator and compare it with the coefficient of performance of a reversible refrigeration cycle operating between reservoirs at the same two temperatures. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the important information requested. By steadily circulating a refrigerant at low temperature through passages in the walls of a freezer compartment, a refrigerator maintains the freezer compartment at -5 degrees C when the air surrounding the refrigerator is 22 degrees C. The rate of heat transfer from the freezer compartment to the refrigerant is 8,000 kilojoules per hour, and the power input required to operate the refrigerator is 3,200 kilojoules per hour. Determine the coefficient of performance of the refrigerator and compare it with the coefficient of performance of a reversible refrigeration cycle operating between reservoirs at the same two temperatures. Let's start to develop the solution. The first thing we need to do for any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement as a bulleted list. A refrigerator maintains a freezer compartment at a specified temperature, and the rate of heat transfer from the refrigerated space, the power input to operate the refrigerator, and the ambient temperature are known. The next thing to do is to summarize what we have to find. This is, again, the same information we highlighted in green in a critical read of the problem statement, presented as a bulleted list. Determine the coefficient of performance and compare it with that of a reversible refrigerator operating between reservoirs at the same two temperatures. The next step in the solution is to develop a schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information that will help us guide our solution. The first thing to note is there is no mass entering or leaving the system. This immediately suggests that a closed system approach is appropriate. Having recognized this important fact, let's select a system boundary. Remember that a closed system does not allow any mass in and out through its boundary. The only transfer allowed through the boundary are heat and work. Here it is selected to follow the physical boundaries as delineated on the schematic with the red dashed line. It encloses the entire refrigeration system and ties in the information provided to the information requested in terms of energy transfers. The rate of heat addition Q.C in the freezer and its temperature, and the temperature of the heat rejection to the surrounding, TH. And finally, the power input into the refrigeration cycle, W.cycle. The next step is to develop an engineering model, in other words, listing a set of simplifying assumptions which will allow us to perform the analysis of the problem. The refrigeration system shown on the schematic is at steady state. The freezer compartment and the surrounding air play the roles of the cold and hot reservoir, respectively. And the energy transfers are positive in the directions of the arrows on the schematic. Having completed all the required initial steps, let's develop the analysis. By inserting the given refrigeration capacity, Q.C, and the power required W dot cycle into the expression for the coefficient of performance of a refrigeration cycle gives us beta is equal to Q dot C divided by W dot cycle, expressed on a time rate basis. The numerical value for the coefficient of performance of the refrigerator we obtain is beta equal 2.5, which is the first answer we were seeking, namely the actual coefficient of performance of the refrigeration cycle. Next, we substitute the given temperature values into the expression for the maximum coefficient of performance beta max equal T sub C divided by T sub H minus T sub C. This gives us the coefficient of performance of a reversible refrigeration cycle. For a refrigeration cycle operating between reservoirs at T sub C equal 268 Kelvin and T sub H equal 295 Kelvin, this gives us a value of beta max equal 9.9. Note that for the expression of the maximum coefficient of performance shown above, the temperatures must be expressed as absolute temperature in Kelvin, not as provided in degree C. This is the second answer we were seeking, namely the coefficient of performance of an equivalent reversible cycle operating between the two specified temperatures. As expected based on the corollaries of the second law for refrigeration and heat pump cycles, the coefficient of performance of the refrigerator is less than for a reversible refrigeration cycle operating between reservoirs at the same two temperatures. This means that irreversibilities are present within the system. To finish the solution of this example, I would like to make a few remarks. As mentioned earlier, the temperatures T sub C and T sub H used in evaluating beta max must be expressed as absolute temperature, namely in Kelvin or degree Rankine, as appropriate. This means converting the temperatures provided in degree C as a preliminary step. The difference between the actual and maximum coefficients of performance, 2.5 versus 9.9, suggests that there may be some potential for improving the thermodynamic performance of the refrigerator. However, while very justified, this objective should be approached very carefully, as improved performance often requires increase in size, complexity, and cost. Quick quiz. An inventor claims the power required to operate the refrigerator can be reduced 800 kilojoules per hour, while all other data remains the same. Evaluate this claim using the second law. You may want to pause the video at this point to answer this question. The claim is invalid, as the system as described by the inventor would have a coefficient of performance beta equal to 10, which is higher than the maximum theoretical value given by the temperatures of the two reservoirs. Hopefully, this is the conclusion you have reached. If not, review carefully this video and derivations and check your calculations. In summary, in this example, we have learned to compute the coefficient of performance limits imposed by the second law for a system undergoing a refrigeration cycle. We have also learned how to use this benchmark to judge of the feasibility of the system and of the presence of irreversibilities within the system. This concludes the step-by-step solution of this example entitled Evaluating Refrigerator Performance.